Now you just taught the scary guy how to solve a series circuit. Now he was quite happy and he was about to go on his way and leave you alone and give you your dollar. But then he realized that there is something else that he needs to know. What if the current has a choice? Whether it will follow one path or the other. What happens then? And this is what happens. So you have to stay there. I guess it will take an hour or two more for you to get back home. So, but you don't want to offend the scary guy, because you want to live. So here's what we'll do. This is one more type of circuit and it's called parallel circuit. What happens here is the charge has a choice. What happens is when the current is flowing, the current is distributed, and these two are the representations of the same circuit. There is no difference here, exactly same. But here it will be easier to understand. Let's say this red current is flowing through and into this circuit, into this junction here. The Kirchhoff's junction rule tells us this red current will be equal to the sum of these blue currents. So this red current is being distributed. Now that's one thing. That will not really help us that much, but what will help us, I'll tell you. But first we will solve this circuit by using the simplest method that we can think of. Later I'll show you the tricks. So for this one, your job is to find the voltages and the currents flowing through each of these circuits, each of these resistances. Voltage is same for each of the branches because as you can see they're connected between two same points. So whatever potential difference will be here will be the same potential difference here, will be the same potential difference here. All the places you will have the same potential difference. Now what is that potential difference? It will be same as the EMF of this circuit. But that's one thing solved. You already know that's the potential difference. So V1, V2 and V3 will be same. And how much is it? V1 equals V2 equals V3, and that's equal to 24 in this case. Now that's not all. The scary guy says, what about the current? Yeah, you have to show him the current. So how to do that? This is the simplest way. When you're trying to find the current through this resistor, imagine that the rest of the resistors do not exist. Let's assume they do not exist. So if you only have 2 ohm and you have the potential difference 24, can you find the current? Yes, you can. I equals V over R. If you ever forget, this is the triangle. V, I, R. So V over R. How much is V? We definitely know how much it is. That is 24. And R is 2 ohm. So it will be 12 volts. 12 volts is the current, 12 amperes. 12 amperes. 12 ampere is the current flowing through this resistor here. Now what about the others? You can find it. This was for the first circuit. While trying to find the current through the second resistor, what you will do is you will consider the rest of the resistors do not exist. So I will cancel this one and I'll cancel this one. Only 4 remains there. This is I2. It will be equal to, here it was R1, V divided by R2, and V is same, that is 24, and R2 is how much? 4. So it will be 6 ampere. It's our I2. How about I3? To find I3, we will consider the rest of the 2 do not exist and that will be this one, and this one do not exist. So you can find it will be V over R3, and that is 24 divided by R3 is 6, and that's equal to 4 ampere. Now there is something strange here that you should notice, and that is the magnitude of current is more where the resistance is less. 12 here, 6 for the fourth one, and only 4 for the last one. So where the resistance is more, the current is less, as in case of 6. Where resistance is less, current is more. That's it for solving for this one with the long method. But there is a cooler and easier method to do that, but I'll show you later. But before that, I want to tell you how to find the combined resistances. So here, if you have a circuit like this, and I'll tell you to find effective resistance, but you will ask me, why do we need to find effective resistance? I will tell you later, because that's very important. That will help you out later. So effective resistance for this one, because these are two in parallel, it will be found by 1 over R effective is equal to 1 over R1, which is 1 over 4 here, and plus 1 over 4. So no matter how many there are, if there is one more, let's say this is 6 ohm, it will be 1 plus 1 over 6. But since we are going to just keep it easy, and I want to show you something cool here, so I'll just take it for 2. 1 over R effective, it will be 1 over 4 plus 1 over 4 is 2 over 4. That's equal to 1 over 2. And if you're going to inverse these two things, you will find R effective is equal to 2 ohm. So what happened here? You have two resistances of same equal resistance, and you find that their effective resistance is half, is not the same, is half of that. So resistance decreased. Effective resistance decreases if you're going to place the resistors in a parallel circuit. But if it were a series circuit, 4 and 4, it will add up, right? It will be 8. That's why in parallel circuit, the current flowing is more. Now comes the, oh sorry, I forgot to show you the trick. The trick is, if you have a circuit like this, I'll just show you the current. You have two resistors. One is 2 ohm. Just take the easy example. And you have another that is 4 ohm. And you got current flowing through it. Let's say 9 ampere. 9 ampere current is flowing inside it. In parallel circuit, current is being distributed. So how will it be distributed? It will be distributed in the inverse ratio of the resistors. So 1 over 2 is to 1 over 4. That will give you the current here. Let's say this is I1 and its ratio in I2. Let's say this is I2. So the current will be distributed in inverse ratio. How does it work? If you're going to multiply both sides by 4, you will get 2 is to 1. This is what you will get. This is the ratio in which current will be distributed. Now the total current you know is 9 ampere. So if you want to find the current here, I1 equals the ratio of it, that is 2, divided by the sum of the ratios, that is 3 times the total, the sum of the values, that is 9. So you will get 2 times 3 is 6 ampere. So 6 ampere current is flowing here, and how much is flowing through here? You can just find it using the circuit, using the same method of ratio, or you can just use the fact that if 6 ampere is flowing here, then that means the 3 ampere will be flowing here, because the total is 9. So you can see that the resistance is less, the current flowing through is more. That's the same thing as earlier, but the trick is it's in the inverse ratio. The current is distributed in the inverse ratio. What else? Okay, this one is easy, but first you need to understand which one is inside which one. The bigger circuit, the combination of these two and this one, they are both in series. So in this case, what you'll have to do is solve this one first. Get the effective resistance of this. Find the effective resistance. How much is it? R, that is for the parallel part, is equal to 1/4 plus 1/4. If you remember what we understood earlier, the effective resistance will be half of each of these resistances. That's equal to 2 ohm. So here the combination is 2. We can just write it as just a simplified form. This is 2 ohm and this one is 4 ohm. So if you want to find the current and voltage of each of these, you can find it now. This is 18 volts. I'm going to solve it by shortcut this time. I know that 18 volts is being distributed into 2 and 4. The ratio will be 2:4, that is 1. Let's say V1 and V2. This is V1, this is V2. It should be in the ratio of 2:4, that's 1:2. 18 is being distributed in that. So we can write 1, what will be 1/3 times 18, and this will be 2/3 times 18. How much is it? This one is 6 and this one is 12. So the voltage here is 6 and the voltage here is 12. That means the voltage across these two is 6 volts and voltage across this one is 12. Will the current flowing through all of these will be same? I don't think so. Let's see. Since this is a series circuit, the current will be found by series method, the main current. Both of these will have the same current flowing through them. So whatever current is flowing here will pass through this one and will be distributed to both of these. So all you have to do is find this one. Once you have found this one, you can just divide it by 2 and find each of these currents, or if they are of different resistances, you can use the ratio, but here we can just find one of the currents. We know that the potential difference across this one is 12, so we can find the current flowing through this one is 12 divided by 4, and that's equal to 3 ampere. So 3 ampere is the current flowing through here. Now imagine this is the 4 ohm resistor. 3 ampere is flowing through this, 3 ampere comes out, and 3 ampere is distributed in this circuit. Since they are both equal, so it will be divided as 1/2. So the current flowing through this one will be 1.5 and current flowing through this one will be 1.5 ampere. So now that you know the potential differences and you know the currents flowing through them, potential difference for this one is, these two actually is 6 volt, because they are in parallel, potential difference across them will be same. For this one it is 12 volts, you have found that, and the current that you just found by using this resistor, you knew the resistor, you knew the potential, you can find the current, and that was 3 ampere. 3 ampere is the one flowing through this circuit, and it's being distributed to both of these, so 1.5, 1.5. That's pretty much it.